I'm doing my professional development presentation on flexible polyhedra, and I'm going to talk about what they are and how you can share this idea with your students. Parts of it are really complex, but there are some fun applications that you could use in your classroom. A flexible polyhedra is a polyhedral surface that allows continuous, non-rigid deformations, and all of the faces remain rigid. So the triangles in this shape are rigid, but the edges are actually what can move. And there, you can't see it on this colored shape, but on the net over here, you can kind of see how this part is concave on this model. And so there are a couple of different kinds of polyhedron, and I'm going to be talking about the non-rigid polyhedron. There are actually rigid polyhedra also. So there was a model that someone created, and this is the video of that model. And it helps to kind of picture what a flexible polyhedron would look like. The edges have hinges on them so that the shape can move a little bit, and parts like right here are concave and other parts are not, but it has to have the concave part in order for this to work, for it to actually be flexible. And so I had a hard time kind of picturing what they were talking about until I found that video, so I thought it was really helpful and would be something you could show your students to help them understand what a flexible polyhedron is. And so the faces are rigid, the edges can be like hinges, so the polyhedron itself is non-rigid. It actually moves around. And the Cauchy rigidity theorem is an explanation of rigid and non-rigid polyhedron, and it shows that in 3 dimensions a flexible polyhedron cannot be convex. So if the faces are made of metal plates and the edges replaced by hinges, a convex polyhedron would actually be rigid. So that's why that one in the video was concave. And it can be shaky, which means it just moves infinitesimally, or it can be flexible, meaning it moves continuously. And there are a lot of little kind of models like this one on Wikipedia and Wolfram Math. And this one is showing a flexible polyhedra that is actually self-intersecting. You can see that these faces in here are crossing over each other. And so the very first examples of flexible polyhedra were discovered by Raoul Bricard, and they're called Bricard's octahedral, and they are self-intersecting surfaces like the one that we just looked at, and they're isometric to an octahedron. And then this was discovered by Robert Connolly in 1977, and the first example of a non-self-intersecting flexible polyhedra was discovered by Robert Connolly, and it was called the Connolly sphere, and it had a triangulation with 62 triangles. And I actually didn't find any pictures or models of this because it's pretty complex. But there is a simplified version created by Klaus Stephan in 1978. And then Maximov in 1995 proved that Stephan's is the simplest possible flexible polyhedron composed of only triangles. And so this would be something to show students some more modern math or things that have been proved more recently. And the Stephan's flexible polyhedra has the fewest vertices possible, and so it's something that you might actually be able to construct with students, just so they can see what it would look like. And they were also referenced as crinkly polyhedra because you can kind of move it around and the paper crinkles. So this website has directions for creating Stephan's flexible polyhedra, and it comes with this net and directions. And it's from a website called Cutout Fold Up, and it's just filled with ideas of things that you can create with paper. So the Bellows conjecture says that all flexible polyhedra keep a constant volume as they are flexed. So this was proven in 1997, so again it's another kind of new idea. And there was a video on this website that shows kind of the concept behind this. And the reason it's called a bellows concept is because here we have the accordion up here, and which is very similar to a bellows that they used to use in like a blacksmith's shop to get fires going. And so here are some examples of the flexible polyhedra again, and then they will show the accordion, and this is kind of the idea about the crinkling of the flexible polyhedra. This kind of demonstrates that too. So if you were to fill this with air, the idea was that the volume remains consistent. And then they also show the same thing happening with a flexible polyhedra. If you were to fill it with air, the volume would be consistent. And so this was a good website too. Unfortunately, if you maximize the video, it's has a lot of Russian text over the pictures, so I just left it small like that. So the Bellows conjecture basically says that the volume must be consistent, and the extended formula for this proof shows that the volume must be a root of a polynomial whose coefficients depend only on the lengths of the polyhedron's edges. Since the edge lengths can't change as the polyhedron flexes, the volume must remain at one of the finitely many roots of the polynomial rather than changing continuously. So it keeps the volume consistent as it moves. So this is the websites that I got most of the information from for flexible polyhedra, and I hope that you thought this was interesting. Thanks for watching.